Today we're going to be doing Chapter 5, Sections 2, 3, and possibly 4. Mathematical induction, which is a little bit of a brain bender type of thing to get through. One of the more challenging aspects of doing proofs. One of the more challenging methods. In natural science courses, deduction and induction are presented as alternative modes of thought. Deduction being to infer a conclusion from general principles using the laws of logical reasoning, and induction being to enunciate a general principle after observing it to hold in a large number of specific instances. Discovery of new mathematical facts often occurs through experimentation with examples, but mathematical induction as a proof technique is not inductive, but deductive. So a little bit confusing there. Once proved by mathematical induction, a theorem is known just as certainly as if it were proved by any other mathematical method. The principle of mathematical induction is, say, P of n is a property that is defined for integers n. Let a be a fixed integer. Suppose the following two statements are true. If that P of a is true, and that for every integer k greater than a, or greater than or equal to a, if P of k is true, then P of k plus 1 is true. Then the statement for every integer n greater than or equal to a, P of n is true. The first known use of mathematical induction occurs in the work of Italian scientist Francesco. That name, I don't know, it's Italian, so I can't pronounce it properly. In 1653, Pascal gave a clear description of the technique. In 1883, De Morgan, known for De Morgan's law, gave the process the name mathematical induction. An equivalent logical inference rule known as the an equivalent inference rule known as the ordering principle. To visualize the idea of mathematical induction, imagine an infinite collection of dominoes positioned one behind the other in such a way that if any given domino falls backwards, it makes the one behind it fall backward as well. Then imagine that the first domino falls backwards. What happens? Well, they all fall down. So if the kth domino falls backwards, it pushes the k plus 1 first domino backward as well. To see the connection between the image and the principle of mathematical induction, let P of n be the sentence, the nth domino falls backwards. It is given that for each k greater than or equal to 1, if P of k is true, then P of k is plus 1 is also true. It is also given that P of 1 is true. Thus, by the principle of mathematical induction, P of n, the nth domino falls backwards, is true for every integer n greater than or equal to 1. Proving a statement by mathematical induction is a two-step process. The first step is called the basis step, and the second step is called the inductive step. So, consider a statement of the form, for every integer n greater than or equal to a property P of n is true. To prove such a statement, perform the following steps. First, the basis step, show that P of A is true. Then, the inductive step, show that for every integer k greater than or equal to A, if P of k is true, then P of k plus 1 is true. To perform this step, suppose that P of k is true, where k is any particular but arbitrarily chosen integer with a k greater than or equal to A. This is called the inductive hypothesis. Then show that P of k plus 1 is true. So use mathematical induction to prove that 1 plus 2 plus 3 plus 4, etc. to n equals n times n plus 1 all over 2 for every integer n greater than or equal to 1. To construct a proof, you must first identify the property n, P of n. In this case, P of n is the equation 1 plus 2 plus etc. to plus n equals n times n plus 1 all over 2. The property is just the equation. The proof will show that the equation is true for every integer. Notice the subject of the sentence is the sum of the integers from 1 to n, and its verb equals. In the basis step of the proof, you must show that the property is true for n equals 1. Now, P of n is obtained by substituting 1 in place of n in P of n. The left-hand side of the equation, P of 1 is the sum of all successive integers starting at 1 and ending at 1, so it's just 1. Thus, P of 1 is 1 equals 1 times 1 plus 1 all over 2. Of course, this equation is true because the right-hand side equals the left-hand side, because 2 over 2 is 1. In the inductive step, you assume that P of k is true for a particular but arbitrarily chosen integer k with k greater than or equal to 1. This is the assumption this assumption is the inductive hypothesis. You must then show that P of k plus 1 is true. What are P of k and P of k plus 1? Well, P of k is obtained by substituting k for every n in P of n. So you have this equation here for P of k. That's the inductive hypothesis. Similarly, you substitute k plus 1 for every n that appears in P of n. So P of k plus 1 is this equation here, or equivalently, this here. A little simplification. And this is what you're trying to show. Now, the inductive hypothesis is the supposition that P of k is true. So how can this supposition be used to show that P of k plus 1 is true? P of k plus 1 is an equation, and the truth of an equation can be shown in a variety of ways. The most straightforward, just about, is to use the inductive hypothesis along with algebra and other known facts to separately transform the left-hand and right-hand sides until you see that they are the same. In this case, the left-hand side of the equation is P is 1 plus 2 plus etc. to plus k plus 1, which equals 1 plus 2 plus 3 etc., to plus k plus 1. By substitution from the inductive hypothesis, you can substitute 1 plus 2 plus etc. To plus k with k times k plus 1 over 2. Since the inductive hypothesis says that's equal to the 1 plus 2 plus 3, etc. to plus k. And then multiply the numerator and denominator of the second term by 2 to make a common denominator. Multiply out the two numerators, adding fractions of the same denominator and combining like terms. So the left-hand side of the p of k plus 1 is k squared plus 3k plus 2 all over 2. Now the right-hand side of the p of k plus 1 is k plus 1 times k plus 2 over 2, which is also equal to k squared plus 3k plus 2. Thus, the two sides of k plus 1, p of k to plus 1 are equal to each other, so the equation p of k plus 1 is true. So the sum of the first n integers for every integer n greater than 1, the sum of the integers from 1 to n equals n times n plus 1 all over 2. A little definition. If a sum with a variable number of terms is shown to equal an expression that does not contain either an ellipsis or a summation symbol, we say that the sum is written in closed form. So, using these facts, how would you evaluate 2 plus 4 plus 6, etc., to 2 plus 500? Factor out the 2, and then do the sum of n integers from 1 to 250, and then calculate from there. Evaluate 5 plus 6 plus 7 plus 8, etc. to plus 50. No, because you can't factor out 5 out of 6 or 7 or 8. Add the first n integers from 1 to 50, and then subtract out 1 plus 2 plus 3 plus 4. Just subtract that out of the result. Okay, let's see here. For an integer h greater than or equal to 2, write 1 plus 2 plus 3, etc. to h plus h minus 1 in closed form. All right, well, we did that, do the 1 to 250, and then by 2, multiply by 2. 1 to 50 minus the 1 through 4. And this last one, h1 or h minus 1 times h minus 1 plus 1 over 2 equals h minus 1 times h over 2. That would be the closed form. All right. Another famous and important formula in mathematics, the formula for the sum of a geometric sequence. In a geometric sequence, each term is obtained from the preceding one by multiplying a constant factor. If the first term is 1 and the constant factor is r, then the sequence is 1, r, r squared, r3, r cubed, etc., to r to the nth power. The sum of the first n terms of this sequence is given by the formula here. R to the n plus 1 minus 1 all over r minus 1. For every integer n greater than or equal to 0, and every real number r not equal to 1. Can't equal to 1 because that would give you a 0 in the denominator. And because r0 equals 1 and r to the 1 equals r, the formula for n greater than or equal to 1 can be rewritten as this here. Okay? In some mathematical contexts, 0 to the 0 power is regarded as indeterminate. In discrete mathematics, we usually define 0 to the 0th power as 1, so that when we write the summation of r to the I equals 0 to n, we do not need to give special attention to the case of r equals 0. So prove that this equation for the sum of the first n terms of a geometric sequence is equal to this here for every integer n greater than or equal to 0 and every real number except 1. Well, in this example, the property P of n is again an equation, although in this case it contains a real variable r. Because r can be any real number other than 1, the proof begins by supposing that r is a particular but arbitrarily chosen real number not equal to 1. Then the proof continues by mathematical induction on n, starting with n equals 0. In this step, you must show that P of 0 is true. That is, you must show that the property is true for n equals 0. Substitute 0 for each n in P of n. So that's both sides of the equation. And then in the inductive step, you suppose k is any integer with k greater than or equal to 0, for which P of k is true. That is, you suppose that the property is true for n equals k. And so you substitute k for each n in P of n to get your inductive hypothesis. Then you show that P of k plus 1 is true. That is, you show the property is true for n equals k plus 1. So you substitute k plus 1 for each n in P of n like so. K plus 1, etc. Or equivalently, k plus 2 here. And that is what you're trying to show. So the sum for any real number r except 1 and any real integer n greater than or equal to 0, the summation is true. Doesn't go into the proof, but I might bring that up on a forthcoming examination. Proving an equality. The proofs of the basis and inductive steps illustrate two different ways to show that an equation is true. Transforming the left-hand side and the right-hand side independently until they're seen to be equal. And 2, transforming one side of the equation until it is seen to be the same as the other side of the equation. Sometimes people use a method that they believe proves equality, but that is actually invalid. For example, for the basis step for 522, they perform the following steps: r to the I, r to 0, and do that. It's not a valid approach. Although it doesn't say exactly why in the slides. I don't know why. Deducing additional formulas. The formulas for the sum of a geometric sequence can be thought of as a family of different formulas in R. One for each real number R except 1. In each of A and B below, assume that M is an integer and is greater than or equal to 3. Write each of the sums in closed form. Yeah. This would be 3 to the M minus 2 plus 1 minus 1, 3 minus 1. So it would be 3 to the M minus 1 to the M minus 1 minus 1 all over 2. So this part would be factoring out the 3 squared to get a geometric sequence here, and then have it 9 times the value of the closed form from part A. As with the formula for the sum of the first n integers, there is a way to think of the formula for the sum of the terms of a geometric sequence that it makes it seem simple and intuitive. Let S of n equal the geometric sequence, the sum of the first n terms of a geometric sequence. Then multiply both sides by r, and then this is the proof, part of the proof at least. Multiply both sides by r, you get r to the n plus 1 minus 1. Now r of n, or r times s of n sub n minus s sub n equals r minus 1 times s sub n. And then equating the right sides of the equation, and equations 5.2.1 and 5.2.2, and dividing by r1 minus 1 gives s of n equals the original equation that you're trying to show. All right. Part 2 of mathematical induction is more examples, which might help get things to sink in a little bit better. Applications of mathematical induction. In this section, we'll show how to apply it in a broader variety of situations. As a first example, consider the argument that the US penny should be eliminated because it isn't profitable to produce. Due to inflation and the rising cost of metals, it actually costs more than 1 cent to produce a penny. If the penny were eliminated and another coin worth 3 cents were introduced, what prices could be paid using only 3 and 5 cent coins? Some examples, not all, because 6 cents could be given out as well, but 7 couldn't. Proposition. For every integer n greater than or equal to 8, n cents can be obtained using 3 and 5 cent coins. Use mathematical induction to prove that for each integer n greater than or equal to 0, n to the n square, n 2 to the 2n power minus 1 is divisible by 3. Okay? As in the previous proofs by mathematical induction, you need to identify the property. In this example, P of n is the sentence 2 to the 2n power minus 1 is divisible by 3. By substitution, the statement for the basis step, P of 0, is P of 2 to the 2 times 0 power minus 1 is divisible by 3. The supposition for the inductive step is 2 to the 2k minus 1 is divisible by 3. And the conclusion to be shown, P of k plus 1 is 2 to the 2k plus 1 minus 1 is divisible by 3. Recall that an integer m is divisible by 3 if and only if m equals 3r for some integer r. Now the statement P of 0 is true because 2 to the 0 is 1 and 1 minus 1 is 0, which is divisible by 3. To prove the inductive step, you suppose that k is any integer greater than or equal to 0, such that P of k is true. In other words, you suppose that 2 to the 2k is minus 1 is divisible by 3. You must then prove the truth of P of k plus 1. Thus, you must show that 2 to the 2k plus 1 minus 1 is divisible by 3. Now, 2 to the 2k plus 1 minus 1 equals 2 to the 2k plus 2 minus 1, which equals 2 to the 2k times 2 to the second power plus or minus 1, or 2 to the 2k times 4 minus 1. Get this back where it was. Close enough. Your aim is now is to show that 2 to the 2k times 4 minus 1 is divisible by 3. Why should that be the case? Both 2 to the 2k times 4 minus 1 and 2 to the 2k minus 1 have a lot in common. And by the inductive hypothesis, 2 to the 2k minus 1 is divisible by 3. Observe what happens when you subtract 2 to the 2k minus 1 from 2 to the 2k times 4 minus 1. You get 2 to the 2k times 3, which is divisible by 3 because it's some integer here times 3. By the inductive hypothesis, this is divisible by 3. So you add this quantity here to both sides because it's a subtraction. And then you get your conclusion. 2 to the 2k times 4 minus 1 is the sum of two numbers that are both divisible by 3. And since both sides are both the sum on the right-hand side of this equation are divisible by 3, hence the sum is divisible by 3. Therefore, the left-hand side of the equation is also divisible by 3, which is what was to be shown. Use mathematical induction to prove that for each integer n greater than or equal to 3, 2 to the n plus 1 is less than 2 to the n. I think that's a type. There's a typo there. Yeah, it's supposed to be 2n plus 1 is less than 2n, 2 to the nth. There's a typo. These slides are full of them. In this example, the property P of n is the inequality shown here. By substitution, the statement for the basis step, P of 3, is 2 times 3 plus 1 is less than 2 to the third power. The supposition for the inductive step is 2 to the k, or 2k plus 1 is less than 2 to the k. And the conclusion is, to be shown, is 2 times k plus 1 is less than 2 to the k plus 1. To prove the basis step, observe the statement P of 3 is true because 2 times 3 plus 1 equals 7, and 2 to the third is 8, and 7 is less than 8. For the inductive step, you assume the inductive hypothesis for that particular but arbitrarily chosen integer, k greater than 3. 2k plus 1 is less than 2 to the k. And then you must show that 2k plus 1 is less than 2 to the k plus 1. With inequality proofs, you can often apply the inductive hypothesis at an early stage. In this case, you can substitute from the induction hypothesis to obtain 2 to the k plus 1 equals 2 to the k plus 2k plus 1 plus 2 is less than 2 to the k plus 2. Something doesn't seem right with that. Yeah, that's right. Multiply out the 2k plus 2 plus 1. So you'd have 2k plus 1 plus 2 is less than 2 to the k plus 2. At this point, you need to think about your goal. You want the right-hand side of the inequality to be 2 to the k plus 1. Since you already know that 2 times k plus 1 is less than 2 to the k plus 2, an easy way to complete your job would be to show that 2 to the k plus 2 is less than 2 to the k plus 1. But this inequality is true because 2 is less than 2 to the k for k greater than or equal to 3, and thus 2 to the k plus 2 is less than 2 to the 2 to the k plus 2 to the k, which is 2 times 2 to the k, or 2 to the k plus 1 by algebra and the law of exponents. Transitivity of order then implies that 2 times k plus 1 is less than 2 to the k plus 1. So the proposition is true. How about a sequence? A sequence, find a sequence A sub 1 is equal to 2, and A sub k is equal to 5A sub k minus 1 for every integer k greater than or equal to 2. Write the first 4 terms of the sequence. Be 2, 10, 50, then 250, kind of a increasing sequence. It is claimed that for each integer n greater than 0, the nth term of the sequence has the same value as that given by the formula 2 times 5 to the n minus 1 power. In other words, the claim is that the terms of the sequence satisfy the equation a sub n equals 2 times 5 to the n minus 1. Prove that this is true. Well, the sequence is 2, 10, 50, 250, because it's a recursive definition where you, for the sequence, you refer to the previous element. To use mathematical induction to show that every term of the sequence satisfies the equation, begin by showing that the first term of the sequence satisfies the equation. Then suppose the arbitrarily chosen term a sub k satisfies the equation, and prove that the next term, a sub k plus 1, also satisfies the equation. So, the proof. Let a sub 1, 2, 3, etc. be the sequence defined by specifying that a sub 1 is equal to 2, and a sub k is equal to 5a sub k minus 1 for every integer k greater than or equal to 2. And the property be the equation a sub n equals 2 times 5 to the n minus 1 power. Use mathematical induction to prove that for every integer n greater than or equal to 1, p of n is true. First of all, establish that p of 1 is true. So just doing the math, you get the definition. It is equal, and the right side, by the definition and the property p of 1. Thus, the two sides of p of 1 are equal to the same quantity, and hence p of 1 is true. Now show that for each integer k greater than or equal to 1, if p of k is true, then p of k plus 1 is also true. Let k be any integer with k greater than or equal to 1, and suppose that the inductive hypothesis is true. A sub k equals 2 times 5 to the k minus 1. Now you show that p of k plus 1 is true. So a sub k equals, or a sub k plus 1 equals 2 times 5 to the k plus 1 minus 1, or equivalently 2 times 5 to the k. But the left-hand side of p of k plus 1 is 5 times a sub k. So by the inductive hypothesis, you can substitute the 2 times 5 to the k minus 1 from the inductive hypothesis in there and regroup, and you get 2 times 5 to the k power, which is the right-hand side of p of k plus 1. So kind of a little side thing. It doesn't this doesn't really matter all that much, but the word polyomino, a generalization of a domino, was first introduced by Solomon Golem in 1954 when he was a 22-year-old university student. Subsequently, he and others have proved many interesting properties about them, and they became the basis for the popular computer game Tetris. A particular type of polyomino is called a tromino, which is made up of 3 attached squares, which can be of 2 types, straight or L-shaped. Call a checkered board that is formed by using m squareds on a side. Observe that if one square is removed from a 4x4 checkerboard, the remaining squares can be completely covered by L-shaped trominos. For instance, a covering of one such board is illustrated here. And they proved that with mathematical induction that for any integer n greater than 1, if one square is removed from a 2 to the n by 2 to the n checkerboard, the remaining squares can be completely covered by L-shaped trominos. I will not be asking you to figure that one out. Yeah, we got time for one more. Four. Then we got, oh, come on now, cooperate. Strong mathematical induction and the well-ordering principle for integers. Strong mathematical induction is similar to ordinary mathematical induction in that it is a technique for establishing the truth of a sequence of statements about integers. Also, a proof by strong mathematical induction consists of a basis step and an inductive step. However, the difference is the basis step may contain proofs for several initial values. And in the inductive step, the truth for the predicate P of n is assumed not just for one value of n, but for all values through k. And then the truth of P of k plus 1 is proved. So, the principle that P of n be a property that is defined for integers n, let a and b be fixed integers with a less than b. Suppose the following two statements are true. P of a plus 1, P of a plus 2, etc. to P of b are all true, the basis step. And then for every integer k greater than b, P of I is true for each integer I from a through k. Then P of k plus 1 is true, the inductive step. Then the statement, for every integer n greater than or equal to a, P of n is true. So, the supposition that P of I is true for each integer I from a through k is called the inductive hypothesis. So, applying strong mathematical induction. The divisibility by a prime theorem states that any integer greater than 1 is divisible by a prime number. We prove this theorem using strong mathematical induction. Prove that any integer greater than 1 is divisible by a prime number. The idea for the inductive step is to, if you're given an integer greater than 1 that is not itself a prime, then it is a product of two smaller positive integers, each of which is greater than 1. By inductive hypothesis, you are assuming that each of these smaller integers is divisible by a prime number. And so, by transitivity of divisibility, those prime numbers also divide the integer you started with. So proof. Let the property be the sentence, n is divisible by a prime number. Show that P of 2 is true. Show that 2 is divisible by a prime number. This is true because 2 is divisible by 2, and 2 is a prime number. So, now show that for each integer k greater than or equal to 2, if P of I is true for each integer from 2 through k, then P of k plus 1 is also true. Let k be any integer with k greater than or equal to 2, and suppose that I is divisible by a prime number for each integer from I from 2 to through k. You must show that k plus 1 is divisible by a prime number. Case number 1, division into cases. If you remember that from previous proof methods. If k plus 1 is prime, in this case, k plus 1 is divisible by a prime number, namely itself. Case number 2, k plus 1 is not prime. In this case, k plus 1 equals a times b, where a and b are integers, with a being between 1 and k plus 1, and b also being between 1 and k plus 1. Thus, in particular, a is less than or greater than or equal to 2, but less than or equal to k. So by inductive hypothesis, a is divisible by a prime number p. So, in addition, because k plus 1 equals ab, we have that k plus 1 is divisible by a. Hence, since k plus 1 is divisible by a and a is divisible by p, by transitivity of divisibility, k plus 1 is divisible by the prime number p. Therefore, regardless of whether k plus 1 is prime or not, it is divisible by a prime number. There you go. How about the sequence S0 equals 0, S1 equals 1, Sk equals 6a sub k minus 1 times, that's supposed to be S sub k minus 1 minus S sub k minus 1, or minus 2, for every integer k greater than or equal to 2. It is claimed that for each integer n greater than 0, the nth term of the sequence has the same value as given by the formula 5 to the n minus 1. So S sub n should equal 5 to the n minus 1. So use strong mathematical induction to show that every term of the sequence satisfies the equation. The basis step must be shown that the first two terms satisfy it. This is necessary because according to the definition of the sequence, computing values of later terms requires knowing the values of the two previous terms. So if the basis step only shows that the first term satisfies the equation, it would not be possible to use the inductive step to deduce that the second term satisfies the equation. In the inductive step, you suppose that for an arbitrarily chosen integer k greater than 1, or greater than or equal to 1, all the terms of the sequence from s through k, s0 through k, satisfy the given equation, and you then deduce that s sub k plus 1 must also satisfy the equation. So, trying to show that s sub k equals 6 s sub k minus 1 minus 5 s sub k minus 2 for every integer k greater than or equal to 2. Show that p0 and p1 are true. That's easily done by substituting 0 and 1 into the equations and comparing them to the definition of the sequence. And we find that they are in fact equal, and they agree with the values given by the formula. Show that for every integer k greater than or equal to 1, if p of I is true for each integer from integer I from 0 through k, then p of k plus 1 is also true. Let k be an integer from with k greater than or equal to 1. Suppose that s sub I equals 5 to the I minus 1 for each integer I with I between less than or equal to k and greater than or equal to 0. We must show that s sub k plus 1 equals 5 to the k plus 1 minus 1. Since k is greater than or equal to 1, we have that k plus 1 is greater than or equal to 2. So, s sub k plus 1 equals 6 s sub k minus 5 times s sub k minus 1 from the definition of the sequence. And then expand those out a little bit, substitute in the hypothesis, and multiply it out and apply the law of exponents, and factor out 6 and do some arithmetic, and you get 5 times k minus 1, which is equal to 5 to the k plus 1 minus 1, which was to be shown. Another sequence with two initial values, a sub 1 and a sub 2 are 0 and 2 respectively. Prove that a sub n is even for every integer n greater than or equal to 1. Well, the first 7 terms are given here using the floor method to determine the index of a that you're using in the equation. And then let the property P of n be the sentence a sub n is even. We use strong mathematical induction to show that the property holds true for every integer n greater than or equal to 1. Show that P1 and P2 are true. Well, the property is true for n equals 1 because and n equals 2 because a sub 1 and a sub 2 are 0 and 2 respectively, and they're both even integers. Now show that for every integer k greater than or equal to 1, if p of I is true for each integer from 1 through k, p of k plus 1 is also true. So the inductive hypothesis is a sub I is even for each integer I, with I being greater than or equal to 1 or less than or equal to k. Now we show that a sub k is even. That by definition, a sub k equals this equation here. Now a sub k over 2 floored is even by the inductive hypothesis because k greater than or equal to 1 and so k is k floored, k divided by 2 floored is between 1 and k inclusive. Thus 3a k floored, k over 2 floored is even because it is a product of an odd and an even number. And hence this equation is even because the sum of two even integers is even. So a sub k is even, as was to be shown. Convention. Let us agree to say that a single number x is a product with one factor and can be computed with 0 multiplications. Prove that for any integer n greater than or equal to 1, if x1, x2, x3, etc. to xn are n numbers, then no matter how many parentheses you are inserted into their product, the number of multiplications used to compute the product is n minus 1. So the truth of the basis step follows immediately from the convention about a product with one factor. The inductive step is based on the fact that when several numbers are multiplied together, each step of the process involves multiplying two individual quantities. In general, when k plus 1 numbers are multiplied, the two quantities in the final step each consist of fewer than k plus 1 factors. This is what makes it possible to use the inductive hypothesis. So, proof. Let the property P of n be the sentence that you're trying to prove here. Number of multiplications used to compute the number is compute the product is n minus 1 with n numbers. To establish P sub 1, we must show that the number of multiplications needed to compute a product of x1 is 1 minus 1. This is true because by convention, x1 is a product that can be computed with 0 multiplications, and 1 minus 1 is equal to 0. So show for every integer k greater than 1 or equal to 1, if P of I is true for each integer from 1 through k, then P of k plus 1 is also true. So for each, suppose that for each integer from I through integer I from 1 through k, if x1, x2, x3, etc. to xi are numbers, then no matter how many parentheses are inserted into their product, the number of multiplications used to compute the product is I minus 1. Show that the sequence there of numbers to be multiplied are k plus 1 numbers, and the number of multiplications used to compute the product is equal to k. Consider a product of k plus 1 factors. When parentheses are inserted in order to compute the product, the sum multiplication in the final one and each of the two factors making up the final multiplication is a product of fewer than k plus 1 factors. Now let L be the product of the left-hand factors and R be the product of the right-hand factors. And suppose that L is composed of I factors and R is composed of, little l factors and R is composed of little r factors. Then L plus R equals k plus 1, the total number of factors in the product. And L is between 1 and k inclusive, and R is also between 1 and a inclusive. By the inductive hypothesis, evaluating L takes L minus 1 multiplications, and evaluating big R takes little r minus 1 multiplications. Because one final multiplication is needed to evaluate big L times big R, the number of multiplications needed to evaluate the product of all k plus 1 factors is equal to k, which was to be shown. So, kind of a little side thing. Given any positive integer n has a unique representation in the form of n equals c sub r times 2 to the r plus c sub r minus 1 times 2 to the r minus 1, etc., until c sub 1 times 2 plus c 0, where r is a non-negative integer. C sub r equals 1, and C sub j equals 1 or 0 for each j equals 0 through r minus 1. That's for binary representation of decimal numbers. Well-ordering principle for the integers. The well-ordering principle for the integers looks very different from both the ordinary and strong principles of mathematical induction, but it can be shown that all three principles are equivalent. In other words, if any one of the three is true, then so are both of the others. So, the well-ordering principle for integers. Let S be a set of integers containing one or more integers, all of which are greater than some fixed integer. Then S has a least element. In each case, if the set has a least element, state what it is. If not, explain why the well-ordering principle is not violated. The set of all positive real numbers. Does it have a least element? Yeah, it's one, isn't it? All positive real numbers? Oh, that includes real numbers, so it's not. So it doesn't have a smallest value, because, and the well-ordering principle is not violated because. Yes, they are. Yeah, it's not rational numbers, it's real numbers, so it's all numbers. The set of all non-negative integers such that n squared is less than n. No, there's no set because there are no non-negative integers such that n is greater than n squared. The set of all non-negative integers of the form 46 minus 7k, where k is an integer. Yeah. 46 minus 7 times 6 would be 4. So that would be the smallest. There is no least positive integer. Least positive real number. No violation of the well ordering principle occurs because well ordering principle refers only to sets of integers. And this is a set that this set is not of a set of integers. And there's no least non-negative integer n, such that n squared is less than n, because there is no non-negative integer. Well ordering principle refers only to sets that contain at least one element. And there you go, k equals 6. 4 would be your least non-negative integer from that equation. And finally, a reminder about the quotient remainder theorem. Given any integer n and any positive integer d, there exist integers q and r such that n equals dq plus r, and r is greater than or equal to 0 and less than d. I don't know how many times they're going to go over the quotient remainder theorem, but it's a good one to remember. And I believe that would be it for the day. Today's Thursday, so have a good weekend. See you on Tuesday for more abstract math fun.